Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the lecture number 2 of linear control systems. In the last lecture we discussed what is the definition of a system. Anything that has an input and an output, that is referred to as a system for the systems engineering. Any series or parallel combination or a feedback combination of multiple systems is also a system. What is a control system? It is a combination of at least two systems, among which one is a controller and the other one is a plant. Plant is a system whose output is to be controlled, and controller is a system that is calculating the input for the plant so that the output of the plant behaves in a way that is desirable by the user. Then the linear system is a system that obeys superposition principle, which involves additivity and homogeneity. So let's continue towards the next lecture. In this lecture we are going to discuss two major types of control configurations. These are feed-forward control and feedback control. Feed-forward control is also known as open loop control or control by compensation, and feedback control is known as closed loop control or control by deviation. So let's first look at the feed-forward control. The main idea of feed-forward control is that we measure the disturbances and generate control signal which compensates their effect and ensures the output. So it's not necessary to have disturbances in feed-forward control, but the most generic form of feed-forward control will have disturbances in it. If there are no disturbances, then we just calculate the input required for the plant based on the desirable output, the information of the desirable output. So this is the diagram of feed-forward control, where you can see here this is the controller. Controller knows about three things: the external disturbances, the internal disturbances, and the reference value for the output of the plant. So based on the knowledge of these three things, controller computes the output that is to be applied to the plant so that the output of the plant may behave in a desirable manner. And then this input of the plant is usually calculated by the controller but applied to the plant through something called actuator. Actuator in real life scenarios might be internal combustion engines or DC motors or AC motors or some other sort of linear actuators or any other thing that applies the desirable signal in physical sense to the physical plant. So actuators, if the actuators are ideal, then whatever the control has computed will be applied to the plant, but the plant also is experiencing something other than the signal from the actuator. This is called internal disturbance. So D1 is the internal disturbance that is also added to the signal generated by the actuator, and the plant input is V instead of U. And then when the plant is generating an output, then the output is also corrupted by another disturbance, which is D2, and after the plant output is corrupted by D2, then we get the overall output of from the plant. So what happens is that controller already knows that if the controller applies based on the information of D1 and D2 and Yref, controller calculates U in such a way that the impact of D1 and D2 is cancelled by this U, and overall Y is equal to Yref. So how do we achieve Y is equal to Yref using the knowledge of D1 and D2? So this is what I'm going to show you next. So in order to show you how this U is going to achieve Y is equal to Yref, we assume ideal actuator. Ideal actuator means that whatever effort control is calculated to be applied to the plant, same effort is applied to the plant. There is no convergent factors or losses in the actuator. Similarly, we assume ideal sensors for disturbance. So whatever disturbance is acting on the plant, whether it is internal or external, it is measured as it is, without any sensor noise or without any inaccuracies in the reading of the sensor. So assuming ideal actuator and ideal sensor, we can apply some algebra to this block diagram. So y here, this y is equal to p times v. V is applied to the plant, so assuming the static transfer function for the plant, which is p, so output of the plant is p times whatever the input is applied to it, and output of the controller is c times whatever the input is applied to it. So if you look at this, then y is equal to p times v plus d2, and if you simplify this, then this is since v is equal to u plus d1, then y is equal to p times u plus d1 plus d2. All of this we get just from the block diagram algebra. So we need y is equal to yref. So how do we achieve y is equal to yref? By appropriate value of u. So rearranging the first of all, we substitute yref instead of y in this equation that we have obtained from the block diagram, because we want y to be yref. So let's replace yref y with yref and see what value of u we get. So then after small rearrangements, you can easily obtain u is equal to yref minus d2 minus p times d1 divided by p. So this is the value of u, which is using the information about yref and information about d2 and information about d1, and along with that it is using the information about the transfer function of the plant, or the you can call it the dynamics, or you can call it the way or mapping of the plant that is converting input to output. So p is a function of an input, it generates the output. So p, whatever p is, so far we are assuming p to be a constant value, so it just multiplies with the input and generates the output of the plant is p times v. So you can see that control can be calculated in order to if u is equal to this value, then we can hope for y is equal to yref regardless of the presence of d1 and d2. So this is how feed forward control works conceptually, and selecting u as in above equation ensures y is equal to yref for this case. Now if you look at the feed forward control from the advantages point of view, then first of all, feed forward control is a simple method. You do one simple calculation and you get the desirable value for the plant, and you only have to apply this input for only one time and then forget about what is happening. Cannot destabilize. So for example, if the plant is stable, stability is not yet discussed in the course, but as the course goes on we will see. For now you can imagine the stability as finite output of the system. So if the system of the if the output of the system remains finite, then we would consider it to be stable. For now you can take this definition, and later on we will go into the more accurate definitions and analysis of stability. So advantage of feed forward control is it cannot destabilize a stable plant, and disadvantages is that we need the sensing of disturbance. Another possible disadvantage is that we need the exact model of the plant. For example, if we do not know what is the exact value of P, then the value calculated for U, which depends upon the value of P, will not be accurate enough to ensure that Y is equal to Yref. So this is basically the main problem in the feed forward control. Feed-forward control is feasible mainly for the systems where there are either there are no disturbances or the disturbances are easily measurable, and feed-forward control is also feasible for situations where we know exactly what the model of the plant is. For example, in the conveyor belt, if the conveyor belt is moving at a constant velocity, then a robotic arm can be used to pick up any boxes which are traveling on the conveyor belt based on just the timing. And you don't have to have any sensors which are trying to locate the position of the box on the conveyor belt and so on. So you can just trust on the model and then apply feed forward control. Okay, then we look at the feedback control. The main idea of feedback control is that we measure the plant output and determine its deviation from the desired value or the reference value, and based on that deviation we apply the control input that basically eliminates this deviation. So this is the block diagram of a typical feedback control system. Now here the difference is that the controller is calculating the input U that is to be applied to the plant. There are disturbances acting on the plant, and there are disturbances distorting the output of the plant, but the actual final output is being measured. And once you measure this, you are feeding it back to the controller along with the value of the desirable. Actually you feed the controller the difference between the actual output and the desirable output. So once you feed this difference, then what happens is that the controller calculates or applies the U that is in response to this difference. And in this case, as long as the difference remains non-zero, the controller will keep on applying the force. So this loop will keep on running forever, and whenever this error is zero, then zero input will be applied to the plant. And if this error later on becomes non-zero again, then the control input will again become non-zero. So this is a continuous loop action going on almost as long as the system is running. In contrast with the feed forward control, where you apply the force only one time. Of course you can repeat the process of feed forward control as well, but a single process is just to whatever your desirable reference is, you just apply this and that's it. And then you can of course repeat this process, but within each process the control effort is applied only once, whereas for feedback control the situation is a little bit more complicated. So for the analysis of feedback control, we will do the same that we did for the feed forward control analysis, that we will assume ideal sensor which gives the same output as is measured, and ideal actuator which applies the same effort to the plant as calculated by the controller, and we will assume the static plant and controller. So assuming all these things, we get again applying the block diagram algebra, y is equal to p times v plus d2 as before, but this time u is equal to c times e. So u here is this input e to the controller times c, and c e is basically the error which is yref minus y. So we will use this to do some simplifications. We separate out the variable y, so we take all the terms involving y to the left hand side, and then we write everything in terms of y. So you can see here that in this configuration of control system, y is equal to p times c over 1 plus p times c into yref, plus P over 1 plus P times C into internal disturbance plus 1 over 1 plus P times C into external disturbance. So this is the situation, and in this situation how do we calculate U, or how do we design this controller so that Y is equal to Yref? So it looks very complicated, but it's easier than it looks, because since we need Y is equal to Yref, how about if we choose C to be very large? What will happen? So if you choose C to be very large, then 1 plus P times C will be nearly equal to P times C. So for example, let us suppose you have 3 million or 5 million rupees. If you add a 1 rupee to 3 million, or if you have like $5 million and you add $1 to that does not make any difference. So 5 million plus 1 is nearly 5 million. So similarly, if C is very large, then 1 plus PC is nearly equal to PC. This one is not going to make much of a difference. Since this 1 plus PC is nearly PC, then PC over 1 plus PC is nearly PC over PC, and PC over PC cancels out and it is nearly equal to 1. So if this term is nearly equal to 1, then Yref is equal to 1, then Y is equal to 1 times Yref plus these things. So what happens to these things when C is very large? So 1 over 1 plus PC, since PC is very large number, 1 over a very large number is a very small number, which is nearly 0. Similarly, P over 1 plus PC is nearly equal to P over PC, and P will cancel out and this will be 1 over C. So 1 over C, since C is very large, then 1 over C will be very small, and this will again go to 0. So Y is equal to 1 times Yref plus 0 times D1 plus 0 times D2. As long as the value of D1 and D2 is not too large, this will work. So this design of controller will work. So you see, in feedback control, all we have to do is to choose C very large. It does not depend upon the value of D1, it does not depend the value of D2, it does not depend upon the value of P, although it does depend a little bit. For example, if D1 is very large, or D2 is very large, or P is very small, nearly 0, then these approximations will not work. But under well designed circumstances, considering the value of D1 and D2 and P, you can choose C as big as you want, and then you can achieve the results that are desirable. So this is the idea of feedback control. And feedback control, where we choose C to be very large, Y is nearly equal to Yref, then this is achieved regardless of the values of the plant and the D1 and D2. If, for example, if there is a little bit of deviation in the knowledge of your plant, or a little bit of a deviation in like we are not even measuring the disturbances here, so whatever the value of disturbance is, as long as the disturbances are not too large, we are all set. So feedback control advantages are reference tracking, disturbance rejection, and robustness. So robustness means that we are able to control the system with good enough performance regardless of the perfect knowledge of the plant. And the next advantage is stabilization. Stabilization is something that we will explore in detail soon when we discuss the stability analysis in this course, and then you will be able to understand stabilization better. For now, you can just imagine that the output, if the output of the plant is not going to infinity, then it's stable in some sense. Okay, disadvantages. The feedback control may destabilize a stable plant. Again, this disadvantage you will understand in detail when we discuss the stability analysis, but for now you can just look at this. So since the control is being applied continuously to the plant, and if there is any error in the value of y, for example, even if there is an error in the sign of y, that is fed back to the controller, instead of minus y, if you have a plus y here, then there will be a lot of mess created by the control action that is continuously acting on the output of the plant. It might take it to infinity as well. So this is just a conceptual demonstration. Later on we will go into the detail as well. So feedback control may destabilize the plant. Feed forward control cannot do that because it's just a one-time action. Need sensor to measure the output of the plant. This is lesser of a disadvantage than the need to measure the disturbances, because disturbances are usually harder to measure than as compared to measuring the plant output. Sensors must be sufficiently precise. This is very important because feedback control relies a lot on the precision of the sensors, and I'm going to discuss this point in detail in the upcoming in the rest of this lecture, because this is very important in feedback control. So for example, let us suppose you have a feedback control and there is some noise in the sensor. So as soon as this noise enters the feedback loop, what you get at this feedback is not just y, you get y plus n. So instead of y, you have y plus n that is fed back to the controller, and now E is equal to y ref minus y minus n. So once this happens, then what happens is that if you apply the same block diagram algebra that we applied before, and we obtained the expression for y in terms of y ref d1 and d2, in this case the expression for y will have an additional term that will be involving n, and n will have multiplication factor of pc over 1 plus pc. So this will cause a lot of problems, because now if you increase C to achieve disturbance rejection, then the this multiplication factors of the disturbance, they will be close to 0, but the multiplication factor of the noise, that will go close to 1. So due to this, so on the other hand, if you try to reduce this PC over 1 plus PC by reducing C, then these factor will start to increase. So trying to get rid of the effect of disturbances results in the amplified effect of noise on the system, and trying to attenuate the impact of noise on the system amplifies the effect of disturbance on the system output. That is the fundamental trade-off in feedback control. So fundamental trade-off in feedback control is that you cannot take care of the disturbance and the noise simultaneously. Once you try to take care of the disturbance, the noise effect becomes prominent, and once you try to take care of the noise, the disturbance effect becomes prominent. So in order to study this trade-off, we define sensitivity function, which is 1 over 1 plus PC, and complementary sensitivity function, which is PC over 1 plus PC. The sensitivity and complementary sensitivity function are basically, this is the impact of disturbance on the system, and this is the impact of the noise on the system. But the problem here is that when you add S plus T, take 1 plus PC as an LCM, you add them, it literally is equal to 1. So what does that mean? That means that no matter what controller you choose, large or small or medium, S plus T is always going to be equal to 1. So if you try to select the controller to make S nearly 0, then T will be nearly 1. And if you try to choose the controller such that T is nearly 0, then S will be nearly 1. So this is basically a representation of fundamental trade-off in control, feedback control. And usually in practical situations, what we do is that we design the control. In practical situations, the disturbances usually occur at low frequencies and noise occurs at high frequencies. So we design the controller in such a way that we keep S nearly 0 at low frequencies and we keep T nearly 0 at high frequencies. So at high frequencies, S is large, but the disturbances do not occur at high frequency. So overall, this S times D1 will be not so much problematic, because at high frequency D1 will be small. And similarly at low frequency, even if this is nearly 1, then but also remember that I am demonstrating this all these properties of feedback control using a simple static case. In general, S plus T are dynamic functions, and this P and C are transfer functions, and we do frequency domain analysis and design. So we will be designing controllers in frequency domain in this course later on. So maybe at that point in course I will try to highlight the impact of S and T when we design the controllers. Okay, so for now you just have to acknowledge this feedback fundamental trade-off that exists in the design of feedback control, and whenever you are designing the controllers, you have to be careful, or you have to be aware of what frequencies your disturbances are occurring at, and what are the frequencies at which the noise is impacting the sensors. Sometimes we have noise filters here added with the sensors. That will increase the cost of the sensor, but that will also increase the performance of a feedback system. So you can see in the market you will find expensive sensors and cheap sensors. Cheap sensor readings are not so accurate. Expensive sensor readings are accurate because they come with all those digital filters, or sometimes in older days the filters were designed using the operational amplifier and other stuff which were analog filters, but nowadays digital filters are more common. That is it for today's lecture. And if you look at what today's lecture was all about, so you can see here that we started with the key takeaways from the last lecture. We went on to discussing the two major configurations in the control systems, which are feed forward and feedback control. Then we looked at the feed forward control and how it works. Usually in general we measure the disturbances, and then we looked at how conceptually you can calculate U using the values of disturbances and the plant. And that's the problem, because if you don't know the plant exactly or the disturbances exactly, then you're not going to achieve Y is equal to Y ref. Then we have feedback control, where we discussed how you can have, if you have large enough control effort, then Y is nearly Y ref. There are some advantages. It can but it can reject the disturbances, it can track the reference, it is robust, because regardless of the complete knowledge of the plant, you can still achieve Y is equal to Y ref. But the problem arises when disturbances are combined with noise. So if the sensor noise is there, then we have a fundamental trade-off in feedback control, and that is studied usually in higher level advanced courses, master's level courses in feedback control system. But at this level, we just while designing the controller, we just make some necessary measures of care. And that is it for today. We'll soon come back for lecture number 3. Thank you very much.